The next type of wave that we're going to talk about is light, and this is completely different from a mechanical wave because light really is independent of any, well, it doesn't need a medium. Light can go from the sun to us through the vacuum of space, whereas sound has to have something to go through, whether it's air or water or some sort of solid thing. Sound needs a medium to disturb. Light doesn't need a medium because light's tricky, light's funny, light's its own little deal. So light is an electromagnetic disturbance. It's a traveling electromagnetic disturbance. And we talk about light two ways, and this may be kind of tricky, but what we say is that it's two things. One, it's a particle. And this kind of helps us deal with not needing a medium. And we see light as a particle in things like its interaction with electrons. That's absorption and emission spectra stuff that you guys talked about. That's absorption and emission spectrum stuff that you all talked about last year in chemistry, where a light wave comes in, hits an electron, and moves it up to a different energy level. It's easier for us to think of light as a particle that way. Another way we see light as a particle is something called the photoelectric effect. In the photoelectric effect, you have different wavelengths of light hitting a piece of metal and knocking electrons off. If you ever want to see that, put a piece of foil or a fork in a microwave. Okay, those sparks are the photoelectric effect. That's kind of how it works. The other way, and the way that we're really going to concentrate on light, is that it behaves like a wave. And this is what we're used to thinking of light as. So for a wave, we see it in diffraction. Talk about that a little bit. We'll see it in reflection, obviously. And we'll see that in refraction. All three of these things sort of give us evidence that light behaves like a wave, like everything else does. We also see light interfere. And that's really what diffraction is all about, is the interference of light. But it acts like a wave. So, for us, this is how we're looking at light. Looking at light as a wave. It's both things, two things at once. It's a weird quantum thing, and if you want to get into that, it may not be a discussion we have in class, but it's certainly one that we can have. So, the thing about this traveling electromagnetic disturbance is that it can only and always ever travel at a certain speed. 3 times 10 to the 8th meters per second. And that's in a vacuum. Nope. 3 times 10 to the 8th meters per second in a vacuum. We use a little c to denote that because it's constant and it always works this way. In fact, this is the universal constant. As we travel through air or glass or water or diamond or a salt crystal or something like that, light's going to move slower. But in a vacuum, this is as fast as it gets. In fact, this is as fast as everything gets. This is our speed limit. Nothing can move faster than light. So, that's light in a nutshell. We're going to start talking about these different things in light, and I'm going to start talking about the electromagnetic spectrum next. This is light. This is its speed. All light travels at this speed. That's how it works. The electromagnetic spectrum. These are all of the things that are light. They're pretty intense. Everything from radio waves that have wavelengths that can be hundreds of meters, tens of meters long, all the way down to things like cosmic rays, which can have very, very, very tiny wavelengths. Cosmic rays, gamma rays, bad for you. X-rays, potentially bad for you. Ultraviolet rays, infrared, microwaves, TV waves, radio waves. All of these waves are a type of light. And visible light, right here, visible light is a small part of the whole electromagnetic spectrum. It goes from 700 nanometers to 400 nanometers. It's 700 times 10 to the negative 9th meters. That's what a nanometer is, times 10 to the negative 9th. So that's visible light. It only takes up a little bit of it. But looking at this, frequency and wavelength share the same relationship. V equals frequency times wavelength. Except for light, it's C. That constant speed of light is equal to frequency. Any light that we can say has 400 nanometers has a certain wavelength. They're associated that way. Now, this is important to note. As the frequency of my wave increases, so does the energy. So cosmic rays carry more energy. That's why you don't want to get hit by cosmic waves. However, radio waves don't have a lot of energy. Right now, radio waves and TV waves and microwaves are passing through you at a very high rate. That's how we communicate. That's what your cell phone is, and it doesn't really affect your body that much. Whereas, you have to wear the lead apron when you get your X-rays taken, and gamma rays cause cancer, and cosmic rays just cause death. They're bad. So as we get more and more frequency, we get more and more energy. But as frequency increases, wavelength decreases. They go in opposite directions, again, because of this whole F lambda thing. If F goes up, lambda has to go down. So, radio waves have the longest wavelength, shortest frequency. Cosmic rays have the highest frequency and the shortest wavelength. Now, visible light. Visible light is a tiny part of this whole spectrum. It goes from here to here on the whole spectrum. That's not very much. 700 nanometers to 400 nanometers. We're talking 200 nanometers. It's not a lot. But it goes from red, orange, we have yellow here, green, blue, indigo, and violet. That's Roy G. Biv. That gives me the colors of the spectrum, the colors of the rainbow that we see. So, in this Roy G. Biv thing, the red has the biggest wavelength and the lowest frequency. Violet has the highest frequency and the smallest wavelength. That's how light's going to work. An easy way for me to remember that this is the high energy side is that UV rays, which are just right here on the other side of violet, tend to damage your skin. Whereas infrared, not that big of a deal. It might warm you up a little bit. So, this is the electromagnetic spectrum. It covers a lot of stuff. This may be something good for you to write down and look at. Color is a little bit different with light than how you learned it in primary school and in art class. Primarily because when we talk about color with light, we're talking about additive color. When we're talking about additive color or combining different kinds of light, we have three different primary colors. For us, we have red as a primary color, we have blue, and we have green. These are our primary colors. I don't know why they are the primary colors, but this is how light addition works. So when we combine red and green, we get yellow. Yellow is red plus green. When we combine red and blue, that's what we mix those two. So magenta is red plus blue. And when we mix blue and green, we get this color here called cyan. And a cyan, again, is going to be blue plus green. Now, when we mix all three colors, we get white light. And that is the mix of all colors. So, when we put red, green, and blue together, we get white. When we put red and blue together, we get magenta. If I were to put magenta and green together, well, that would give me white because I'd have all three colors. If I were to put yellow and cyan together, I'd get, well, yellow has red and green, cyan has blue and green, so I'd get a greenish white light. That's how additive color works. We combine them for more and more and more and more colors. So just as a note over here, we're going to say that magenta is equal to red plus blue, cyan is equal to blue plus green, and yellow is equal to red plus green. This is how additive color works. So this brings us to what happens when we see something. Well, let's say we have an object that is red. We have a red object. And let's say we shine white light. Nope, that's red light. Let's say we shine a white light onto that object. Well, white light has all the primary colors on it. So it's shining red light onto my object. It's shining blue light onto my object. And it's shining green light onto my object. What it means to be red is that only red light is reflected. That's what it means to be red. Red objects absorb green and blue and they reflect red. If we were to shine just green and blue light onto a red object, it would appear to be colorless or black. That's what lack of color is when we're adding light together. Same thing works for a cyan object. I'm sorry, that's magenta. Same thing works for a magenta object. Let's say I shine my white light onto my magenta object. That's not magenta. So we got red light, we got blue light, and we have green light shining onto my magenta object. In this case, the two colors that come off are blue and red. That's how we see colors. White light is absorbed by something, and only certain colors of light are reflected off, are given off. That's how we see color. A green object would absorb everything that's red and blue, and only green would be reflected from it. A yellow object absorbs blue and reflects everything else. A white object would be reflecting all kinds of light. But we would see these things coming off of it. That's how we would perceive color. That's color. Reflection. Reflection is a pretty cool principle, but it's pretty easy. Imagine we have a flat reflecting surface. We're going to have a ray of light come into that flat reflecting surface. We call it the incident ray. That's the incoming light ray. Once it hits the surface and is bounced off, we call it the reflected ray. I don't know if I have to define that for you, but that's the ray that's reflected off. Now, we don't measure this angle. We measure according to the normal. We'll go ahead and define that. The normal, and we're used to seeing the word normal, especially in this context, is a line that is 90 degrees to my surface. So angles are measured with respect to, that's WRT, the normal. So the angle of incidence and the angle of reflection are measured with respect to the normal. This gets important when we talk about curved reflecting surfaces, and I'll show some of those in class, but it's reflection with respect to the normal. And for reflection, we have that the angle of incidence has got to be equal to the angle of reflection. If this thing comes in at 45 degrees, guess what? It has to leave at 45 degrees. That's how all reflection works. That's how all reflection works. So over here we have a simple example of reflection. I'm going to use thinner lines here. So we're going to draw a couple of rays coming off of our object, mostly the top of it. So imagine a ray of light coming off the top of this object hitting the mirror. Well, it's going to be reflected in such a way that this angle and this angle are the same. And if we imagine another one coming in and being reflected out, it's going to work in such a way that those two angles appear to be the same. Now, we're going to talk about why we see a reflection. So you're going to have to deal with it. I'm not great at drawing eyes, but let's pretend this is an eye, with eyelashes and all that stuff. As you see these two bits of light, what you do is trace them back to where they might be coming from. You trace them back to a potential source. And what you see is a place behind the mirror where those rays appear to be coming from. And behind the mirror, this is a terrible illustration by the way, behind the mirror, your eye forms an image. But this is a little bit unique. This is a virtual image. The reason it's virtual is because light rays do not cross to form it. It's virtual because it's your eye tracing these light rays back to where they come from. That's just how your eye sees things. At the same time, looking here, we have two rays coming off of it. When your eye sees it, it only sees these rays and traces it back to the place where the actual object is. That's a real image. It's a real object. But it's a real image because light rays cross. That's how we get real images. Virtual images happen when our eyes trace light back. They trace light back into something. This is a mirror. There's nothing behind it. Our eyes trace the light ray back to it. But that's why we see the exact same image. This law of reflection tells us how the things will be, how they'll look. And that's reflection.